Hi, welcome to my channel, JaberTime, where I do math videos from algebra to calculus and differential equations, simplified with examples. If you like this video, hit the like button and subscribe. If you have any comments or questions, leave them down below. And once again, I want to thank you for watching and hope to see you again and again. Thank you. What derivatives tell us? How could you take advantage of knowing enough about derivatives in different intervals and different locations, mainly using graphs, or the benefit of that applying it to the graphs? Let's be practical and take a look at some notes and explain it. To start with, increasing and decreasing functions. Well, this is just like a basic definition of increasing and decreasing. If the function is increasing and you have x2 greater than x1, that means you're going from a to b, like to the right side. F of x2 is greater than f of x1. As you can see, it's higher than the value of f of x1. We say that the function is increasing. Now here, f of x1 is greater than f of x2. The value of f of x2 is a lower level. So f of x2 is less than f of x1. We say f of x is decreasing. Now, the graph says it. If the graph is increasing, we have tangents that look like this, which means f prime is positive. If the graph is decreasing, it could be going like this, but just an idea to get started. If the graph is decreasing, the tangents are taking you down, which means f prime, because those tangents, their derivative represents slopes. The derivative is negative, the slopes are negative. Okay, let's add more, because from now on, most of the math is connected. So I don't want to just talk about increasing, decreasing. I have the graphs handy, so I'll take care of more on the same slide. If you find the second derivative for this function that already graphed, you're gonna find that it's negative on the interval that you have. Concave down. So when double prime derivative is negative, we expect that the graph is concave down. If f prime, double prime I mean, is positive, we expect that the graph is concave up, opens up. Keep that in mind. So now we're talking about decreasing from the point of f prime being negative. F double prime gives you concave up and concave down. Here's more notes. We sometimes graph a line. We call it the first derivative sines. That's what we call it. And sometimes we make a line also for f double prime sines. From there, we could make notes and take it to the graph and start graphing. If f prime is positive, we say it's increasing. If f prime is negative between 1 and 2, we call the graph decreasing. So which means at 0, where it changed from being positive to being negative, we have a local max. Alright? Now, if f prime is 0, those are positive 0, negative, and so on and so on. Now, f prime at 1 is 0. At 2, it's 0. At 3 is undefined. At 4, it's 0. That means these points are called critical points. Here I added as undefined. Doesn't have to be always 0. That means it's a sharp edge. That's what it means, especially if it's connected and continuous. Now let's go back right here. Negative means decreasing. Negative again decreasing. So it went down, then slowed to make a horizontal tangent, then went back down again. I have a graph to show you more of what do I mean by this. It's not always like it alternates positive, negative, positive, negative. It could happen, negative, negative. Going down, going up because it's positive, going down it's negative. If it's going down and going down, this is a critical point, but it's neither local max or local min. Here, we're going up, then we're going down, so at 4, we're going to call it local max. Now, it depends on other things. If this is continuous all the way, to call some of them are absolute max or min. But let's just stay focused on what does f prime tell me. Look at f double prime. If it's negative, concave down, positive, concave up, negative, concave down, negative, concave down again, positive, concave up. When you set f double prime equal to 0, you find, for this example, for this nodes, at 1 it's 0, at 2 it's 0, at 3 it's undefined, at 0, at 3 undefined, I mean, 4, at 4 it's 0. Now, if f double prime changes sign from negative to positive, we call this point not critical point, we call it inflection point. If it changes from positive to negative, we call it inflection point. If it doesn't change sign from negative to negative, we don't call it inflection point. It changed from negative to positive, we call it inflection point. Let's take a look at more notes and examples. This graph is going up, then as you could see it's a sharp edge going down, up, looks like this, slows down, then goes back up. Kind of like a behavior of cubic right here. To refer, if I want to use numbers, I have 1, 2, 3, 4. Here's f of x. I'm writing the notes in one page so I could go back and forth and connect. Increasing, decreasing, increasing, increasing. Yes, I could see that. Increasing, decreasing, increasing, increasing. Look at f prime. If you find f prime, I don't have the function here, it's notes. F prime is positive. That agrees with the word increasing. F prime at 1 is undefined. Critical point. F prime between 1 and 3 is negative. That means the graph is decreasing. F prime between 3 and 4 is positive, increasing. Then f prime here is 0. F prime at 4 is 0. At 4 it's 0. We call it critical point. But went from positive to positive, from increasing to increasing again. So it's no extrema. It's not a max and it's not a min. So when it goes up, then it goes up again, that's what happens. Something like that. So we don't call it a local max or local min. No extrema. This is a local minimum. This is a local maximum. Why is that? The graph says it, but f prime, if you're increasing, then decreasing, that's a local max right there. If it's decreasing, then back increasing, here we have a local min as it shows. Let's look at f double prime. F double prime says positive to the left of 1. Yes, it's concave up to the left of 1. Positive between 1 and 3, still concave up. Between 3 and 4, positive. After 4, positive. Concave up, concave up. It's concave up in all 4 pieces. we say f double prime is positive, that means concave up, and f double prime is negative, that means concave down. Here's an example, and the last one will cover more details. Graph that goes up, down, back up, that's kind of cubic, and it's written now here for me. 2x cubed plus 3x to the second plus 1. When you find the derivative, it's 6x to the second plus 6x, which could be factored by taking 6 and x out from both, and you end up with x plus 1 inside. Set it equal to 0 because that's how we play the game. We always find derivatives, find them equal to 0. Even if the first function, if you can find it or solve the zeros of it by making it equal to 0, that means you're looking for the x-intercepts. Any hint, any idea will help, anything. So sometimes we let f of x equal to 0. We go after f prime, we let it equal to 0. We go after f double prime, and we make it equal to 0. In this case, I'm focused on f prime to equal 0. By looking at the factored form, I have 0 and -1. So we call these ones critical points. While we are into it, let's find f double prime. F double prime from here will give you 12x plus 6, which is right there. Factor 6 out, I get 6 multiplied by 2x plus 1. Set it equal to 0. I get -1 over 2. Only one value, -half. You can see the -half in blue right there, and the 0 and -1, 0 here and -1. Here's f of x, here's f prime, and here's f double prime. F prime, here's f prime. Plug in numbers. We found the zeros of f prime, which is 0 and -1, 0 and -1, and I'm trying to align them, as you can see with the graph. Here's -1, as you could see, and -half is somewhere here. So you can just go back and forth and connect. So we have a critical point here at -1 and 0. Plug in anything between -1 and 0, because if you're crossing the x-axis here and here, they're called zeros. So either you were down, then we went back up. So if it's negative, it's going to be negative for any number that you pick. Here, kind of like above, below, or the other way around. So just test it with numbers and you should be fine. Positive, that means increasing. I wrote it up here. My function is increasing. Negative means decreasing. I wrote it down up here, I mean. Positive means increasing. So my function, so far, I know that it's increasing, then decreasing, then increasing. Yeah, it looks like it. Increasing, decreasing, increasing. Now, how do you go this way or do you go this way? Are you concave down or are you concave up? Well, that's why we need f double prime. To the left of -half, plug in numbers. Right here or here, you're going to end up with negative. So it's concave down. You see it's concave down. After -half, plug in numbers. For the convenience, you could plug in any number. Let's plug in 1 after -half. Here we go. 12 times 1 plus 6 is positive. Yes, positive. So it's concave up. After -1, it's concave up. Because it's changed concavity at the location of -1, this point is called inflection point. Sometimes we describe it as the weakest point of the graph. Inflection point at x equals -half. I think that should do it, and that kind of like a simple example that covers a lot, as you could see. We're going to take a detailed example and we're going to end up the video. Here's a last example. My function is 2x cubed plus 3x to the second plus 1 in red, 3 pieces, cubic. The first derivative is 6x to the second plus 6x, which is graphed also, as you could see, in green. if you factor 6x out, and you do the math, it's x equals -1 and 0, -1 and 0. Double prime is x equals -half when it's equal to 0. And this is kind of like a simple notes for our previous example. F increases, decreases, inflection point is gonna happen right there. Concave down. I'm putting more numbers here in detail. As you can see, I plugged in 1, I plugged in -1. You could plug in whatever you want. At -half, we have inflection point. F prime, which is a parabola that has 2 zeros and opens up because the leading coefficient is positive 6, looks like this. If you pay attention differently from the graph without plugging numbers, take a look. The values between 0 and -1 are below the x-axis, so f prime is negative. The values of the parabola, which is called f prime, to the right of 0 is above the x-axis, which means positive values. The values to the left of -1, because I live above the x-axis, has positive values. Alright? Or you could just plug in numbers to test if it's positive or negative. Kind of like giving you more details. Hopefully those examples are helpful. I think about 17-18 minutes for a video like this, it's good enough. I don't want to make it 45 minutes. As you could see, it's going to be too much to go over, like too many graphs to get to the point. The point is the same thing all over. You just have to practice and keep all these words back and forth with you. Alright? Thank you for watching, and I'll see you on the next one. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.